which doesn't exist for the quartz fiber post. The quartz fiber post, the highest stress was on the surface of the tooth root. So we predict a higher stress in the tooth for the case of the zirconia post, and you might expect then a lower lifetime for teeth reinforced with the zirconia post. And then comparing the tapered design with the two-stage design, we predicted that in the case of the, I'm forgetting now. I think it's in the case of the two-stage design, we predict a lower stress than in the case of the tapered design. And we used the step stress method to then verify our predictions. We divided the specimens into 3 groups. And one group is subjected to this on the y-axis is how hard the mechanical load frame is chewing, masticating on the specimen over time. And so we see that the initial cycles are chewing very lightly, and that it's a very stronger and stronger test as time goes on, and then it reaches a point where we stop going higher and we continue to test the specimen at a constant load level, constant load amplitude over time until all of the specimens have failed. So this is our rapidly increasing group. And then we also had a slow increasing group where we only increased the bite force by a little bit, and then we kept the bite force to be constant over time until we had a few specimens that did not fail and increased it rapidly at the very end. And in between, a third of our specimens were subjected to moderate loading, where we had a low and constant bite force over time, and then the load amplitude was increased slowly at the very end. And so this is what we typically do in the step stress method, is we divide our specimens into 3 groups, and we have an aggressive and a non-aggressive and a moderately aggressive load profile over time. And you can see the result of the data there. And we predict the blue is the zirconia ceramic post with the tapered design. Okay? And comparing that to the orange is the fiber post with the tapered design. And if we come, this is the probability, unreliability, or probability of failure. If we come down to what we want, a very low probability of failure, around 5%, we will see that the orange group, the fiber post group, is predicted to last longer than the blue group, the ceramic group. And we see the same thing when we go to the two-stage design. The magenta line, pink line here, is the fiber reinforced, and the black line is the zirconia post. And when we go down to a low 5% or lower probability of failure, the magenta, the fiber post, has the tooth lasting a longer time. So it's confirming the finite element predictions. And then also comparing the 2 designs of the posts, we can compare that too. And so looking within ceramic, let's see. We have blue is the tapered design, and black is the two-stage design. And so black is further to the right along the x-axis. So at all probabilities of failure, the two-stage design is lasting longer than the tapered design. So that's the type of analysis you can do. However, in our attempt to speed up the research, we don't want to stay so focused on the acceleration that we forget to think about other problems that may be caused by accelerating too quickly. And you always have to remember not to focus on your objective too much and forget about what may be sneaking up behind you. We don't have any of those in Mississippi. And one of the problems that can sneak up on you when you do efficient tests and you test more and more rapidly in vitro tests is the uncertainty you get from extrapolating to the clinical case. Obviously, the faster we test, we are testing farther and farther from the clinical case. And extrapolating farther reduces the statistical power, and it increases the 95% confidence interval of our prediction. So we result in uncertainty. And what I'm trying to show you here is that if we have a low level of bite force and a high level of bite force that we are testing at in vitro, and we are stretching from those two foundations of knowledge to reach way out to the clinical case, it's a dangerous situation, like when you're on a ladder with two supports and you're reaching very far to replace a light bulb. And so the farther you reach, the more danger you are in of making a mistake or making an incorrect prediction. And also Dr. Nelson, who developed the step stress method, later developed this idea of the acceleration factor, which is in terms of the distance between the most rapidly tested specimens in vitro and the clinical case, and the distance between the most rapid and the slowest specimens tested in vitro. And this tells how fast you're extrapolating, how much you're accelerating, how much danger you're in of making an incorrect prediction. One way to reduce the danger of reaching out to the clinical case is to move our ladder closer to the objective. That makes it a little bit safer. However, this will result in both the low bite force and the high bite force specimens tested in vitro. Both of those will be tested at lower bite force than before, and so they will last longer. So that makes sense that if you test for longer periods of time in vitro, you can have more statistical power for your predictions. And that's not much help because we want to accelerate things. So another way that you can make the ladder more stable is to spread the legs of the ladder far apart, right? And so we can make the high bite force specimens tested in vitro in the same level, but the low bite force specimens will be closer to the clinical case, and this broadens the base of our ladder, and it decreases our acceleration factor and increases our statistical power. And in this case, these specimens will still be tested very rapidly, and these ones will take longer to observe failures. We may have a bunch of run-out specimens. But we can also broaden the base of the ladder by keeping the low bite force specimens at the same as original level and instead increasing the high bite force specimens. And this has the result of making the entire test take less time, actually. These specimens will be tested very, very rapidly. It increases slightly our predictive power, and this is obviously the way that we want to go in our fatigue test design. It takes less time and it provides more statistical power, but we start running into another type of possibly unforeseen obstacle. And when we get into this red danger region, that's the region where we can have a change in the mode of crack propagation or a change in failure mode so that we are not observing the same type of failure as would happen in the clinic. So that was the source of the question I asked earlier about when we chew at a very high bite force in the load frame, are we changing maybe the ratio of the crack propagation modes? And we can see that, for example, in metals. If you are testing implants in fatigue, then we see that the lifetime number of cycles to failure, or lifetime NF, follows an inverse power law with the stress cycling of the stress, and it follows this inverse power law called Baskin's law below the yield strength of the material. If you accelerate too quickly, you will go above the yield strength of the metal in some locations. And if you do that, the data will still follow an inverse power law, but they follow a different inverse power law, which is based on the fluctuation in plastic strain, not the fluctuation in stress. The data will still fit very nicely in your computer model, and you will think you have good results, but you will be predicting a different failure mode, the time for a different type of failure mode than the one that will actually be observed in the clinic. And so your data will have no predictive power, actually. That's a very dangerous situation. And if you're lucky, you can detect that. If some of your specimens are tested above the yield strength of the metal, and some are tested below the yield strength of the metal. That will become very apparent when you fit your data to the model. And this happened in the past year in our laboratory when we were testing implants in fatigue. We fit the data to this model that predicts lifetime as a function of load amplitude. And we get this type of, the red line and the green line are the 95% confidence interval for our predictions. So we got this huge confidence interval, meaning that we have no certainty, no predictive power. And even you can see the confidence interval curls back on itself. So we are not making a good prediction here. When we predict out here to the clinical case in 10 million or more cycles, we have no idea what stress level that's going to be at exactly. And if we look at the Weibull modulus for that analysis, the Weibull modulus is basically 0. And for those of you familiar with Weibull statistics already, you will know that the higher the Weibull modulus means the more reliable your prediction is about how long something will last or what level of stress it will fail at. Okay. So we are having very little predictive power here. But then after we did a finite element model to determine what type of bite force we're limited to avoid reaching the yield strength anywhere in the implant, we eliminated the specimens from the analysis that were tested above the yield strength and did the analysis again. And only in high cycle fatigue specimens, and we get a very tight 95% confidence interval because we're testing now only with Basquiat's law. And Weibull modulus raised to 3.1. And those who are doing fast fracture Weibull analysis may look at a Weibull modulus of 3, and they will say, oh, that's very low. I expect to see 8 or maybe 10 or 20 from a high Weibull modulus. And I have to caution you that when we talk about lifetime statistics, that Weibull modulus tends to be between 1 and 3. So a Weibull modulus of 3 is a very high Weibull modulus for lifetime predictions. Okay, so we have talked about so far having the load frame chew at very high mastication load, higher than we use in the clinical case. And this is only one method of accelerating the lifetime testing, and that's known as overstress acceleration. That's with a very high bite force, overstress acceleration. And we talked about the extrapolation uncertainty, the changing failure mode, possibly. There is another type of acceleration we can use. If we reach the heaviest bite force that we can use in a clinically relevant test, and it's still taking too long to test our specimens, then we can invoke usage rate acceleration. Usage rate acceleration has 2 methods, 2 means to accomplish that. One of them is the type of method they use when they test your appliances in your home to see how long they are likely to last. So in the factory where they test dishwashers, they have a quality control team which is running dishwashers around the clock. In your home, you will probably run the dishwasher 1 time per day. But in the quality control lab, they're running the dishwasher 20, 30 times per day, non-stop. And this is one type of usage rate acceleration. It's cutting out the inactive periods of time to provide continuous usage, and we can get the test done faster that way. So having the load frame chew day and night on the specimen. And then another method is increasing the frequency of the cycling. So how fast would the typical patient chew their food? Maybe I've seen estimates 1.2 times per second up to 2 times per second, 1.2 to 2 hertz. Frequently, specimens are tested at a faster frequency than that. 4 hertz is a very frequently used frequency, and I know Bob has tried recently to go up to, what was it, 30? That's right.